Now, as was just said, read in this next paragraph. Of course, most populations are constrained by limitations on resources, even in the short run, and none is unconstrained forever. The following figure shows two possible courses for the growth of a population. The green one is exponential growth. The blue one reflects what you just mentioned, namely a population that starts off growing like the exponential curve, but soon diverges from it and is constrained by what's referred to as the carrying capacity of the environment. Now, where does this curve come from? There are different ways you could answer the question. One is, I think that's what the population will do. So you just drew it. A way you can derive this is by changing the model. Instead of the rate of change of the population just being proportional to the population, you change the formula for the derivative. And what we do in Math 115 is we come up with this, and we explain where this symbolism comes from. You don't just pull it out of the hat. It might seem like that the first time you see it, but you stare at it long enough, and this becomes a sensible sort of mathematical expression. It says that you modify the rate of change by multiplying the factor that you had before by something that accomplishes mathematically exactly what you wanted to accomplish with the carrying capacity. And this gives rise to a different kind of solution. And what's really amazing, this is an extremely simplistic model. But the person who developed it wanted to apply it to the US population. So the data points used to develop the equation were just these 6 plus assumptions that led to that form for the derivative. And this would give rise to the red curve. The data points are just the blue points. They stopped being real in 1840. But it stayed accurate until 1940. Those are the US population dots following his red exponential they're just the growth curve. But then, oh darn. There it goes. The US population takes right off after about 1945 or so. Certain significant historical events might explain part of what happened here. But it's pretty clear that his graph stopped being a good curve. Oh, I just wanted to show you. Sometimes exponential growth is sensible for quite a while. This is a picture, oh, it's a very bad picture, of an algae bloom off the coast of China. Now, this is caused by both chemical and heat pollution. It's stunning in its size. It's also deadly because algae consumes oxygen, which means it's not available for any other organism. And sometimes you just have to wonder, what are they thinking?
Oh my God. Oh, no, we don't do that.
Algae's got a lot of sort of biological activity going on. It's not like swimming in some kind of sterile water. If these guys have any cuts, sores, or whatever.
So guys, the interesting thing here, if I could just interject for a second, is between the three of us, we each see this picture and each see different things. I look at the biology that's happening here and think about the toxins that this algae is producing, as well as the amount of oxygen that they're consuming. Dr. Duffus looks at it and might be considering some of the mathematical equations that are happening here, the growth of the algae, things like that. Dr. Gordon looks at it and sees, what do you see?
I'm thinking about the population and what would, who is going to be swimming in this water, and why would they be swimming in this water, and what the motivations would be.
And this is all part of you becoming a scientist. As you become a scientist, you will look at this and you will see different things just like we do that interest you and go, I could study that for a while, and I think that's really cool and amazing. And that's something that we're going to talk about more as you go through GLUE. Sorry.
Oh. Okay, so. Oh yeah, this is all really taken. So I'm going to do this quickly. I think it's fun. So, have you ever had the anxiety dream you realize you've forgotten to take the final in a course? Or you're about to take the final in a course you've forgotten to go to?
Everyone.
For professors, it works the other way around. You dream you're giving a lecture for a class that you know nothing about. Closer to the truth than you may want to think.
You're not supposed to find that out till later.
But one area, namely the second main area where math gets applied, is probability theory. And this is one of those things that a lot of mathematicians don't study very much themselves. And when they first come to teach it, it can be quite confounding. Perhaps the most pulse-quickening topic of all is conditional probability, the probability that some event A happens given that some other event B has happened. It's a slippery concept, blah, blah, blah. No, just scan this last paragraph. Before going on vacation, you ask your spacey friend to water your ailing plant. Without water, the plant has a 90% chance of dying. Even with proper watering, it has a 20% chance of dying. The probability that your friend will forget to water is 30%. What's the chance your plant will survive? If it's dead, what's the chance your friend forgot to water it? If your friend forgot to water it, what's the chance it will be dead? Now, my reaction to reading this was it would be easier to either get a new plant or get a new friend, rather than to figure out what's going on with these conditional probabilities. However, I can't resist. So, let's just do something simple. And then I'm going to show you how you might apply it to something a bit more serious. And we'll only take them. So conditional probability. I know these card things. I'm going to turn over a card, not replace it, turn over another. What's the probability both cards are aces? Now, there's lots of ways to think about this and to figure it out. I want to illustrate one. We make something called the decision tree. And card games are the simplest, maybe flipping coins. These are the simplest sorts of problems. Now, along the edges of the tree, we're going to put probabilities. The probability of the event at the right hand occurring. So what's the probability? Oh, for those of you who've never seen a deck of cards before, 52 cards, 4 suits, aces through kings. What's the probability of turning over an ace? 1 out of 13 or? Right. a lovely thing about decision trees is when you add up the probabilities branching from a point is they add up to 1. The probability of not getting an ace, 48 out of 52 or 12 out of 13. Now, the hard part. Second card. Ace, not ace, ace, not ace. The probability of getting an ace, given that you had an ace the first time. 51. Guys have spent too much time gambling probably. 48 out of 51 the other way. These are called conditional probabilities. Probability second is ace, given first is ace. So I'm just abbreviating this randomly. And then down here, the probability the second is an ace given the first isn't. 4 aces, 51 cards, and you did 47 of them. Now, there's only one way to get to 2 aces, and that's to follow this branch to the end. And we multiply the 2 probabilities along with it. 4 out of 52 times 3 out of 51. What we're actually multiplying is the probability that the second is an ace given that the first is an ace times the probability that the first is an ace. And that's equal to the probability that first is ace and second is ace. Okay, moving up the sleeve. No, haven't done anything illegal yet. Okay, so now we're going to do something else. The probability of having a disease, leave it unnamed. It's fairly uncommon. 0.8% of the population, 0.008. So we have a population, the disease proportion is just 0.008 of the entire population. I'll tell you some more information. The probability of a positive test, so this is the kind of disease for which there is a medical test. The medical test isn't foolproof. The probability of a positive test, given that the disease is present, is 0.90. So I'm making these up. This has got a name. In the literature, this is called the